Next on Exploring Space.
I think that the question of whether there is intelligent life beyond Earth is essentially the same question as whether there is life beyond Earth.
And the thought that in this incredible enormity, that we are the only creatures able to look at it and understand something and to talk about it, that would be a very discouraging thought. That would be a depressing thought.
Ultimately, we're only around until the next big impact, and then human civilization is gone.
Sometime in the future, we are going to be sending a submarine into an alien ocean, searching for life.
Fundamentally, the biggest challenge to getting humans to Mars is money. The technology is here. We can do it.
I see Mars as the first testing ground of the possibility that life has a future in space.
RCO, report range, go for launch.
Range is go for launch.
LCDR, this is LVD, go for launch.
Roger.
July 2003.
On.
The United States prepares to send a robotic land rover to explore the planet Mars.
20 seconds.
The quest, to hunt for water and for signs that humans are not alone in the universe.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, main engine start, 0, and liftoff of the Delta rocket with Opportunity.
The transient's at liftoff. Engine position looks good. Recovering nicely from the liftoff transients, and the solid rocket motors are increasing their thrust during their 75-second burn. Main engine chamber pressures holding steady.
The heavens above have long been a target for exploration, for determining humanity's role in the great scheme of things. Some find the answers in religion and spirituality. Others find comfort in the hard facts of science. Earth may be a rare environment, uniquely designed for nurturing living organisms. But as humans explore the creation of the planet, the realization grows that the answers to the origins of life may lie beyond earthly bounds.
Nobody knows how or when life began on Earth, and really the only way that you can begin to evaluate when or how life began is by examining the geological records.
Dr. Stephen Moses of the University of Colorado is examining some of the planet's oldest rock here in Greenland at the top of the planet. When Earth was originally formed, it was a ball of molten rock, so hot no organic materials containing living organisms could have survived. As it cooled, the Earth would have consisted only of sterile oceans and barren rock.
The early Earth's surface was not rich in organic compounds. It was a surface that was dominated by compounds that are not particularly helpful to get life started.
And if no organic material could exist on such a barren planet, life on Earth may have started elsewhere.
My personal opinion is that since space is so rich in these organic compounds, it must have played a role. I don't think it's unreasonable to invoke the space medium as a source area for raw materials to get life started, because after all, space is close. Space is only about 30 kilometers that way. All you have to do is take material from up there and bring it here. That's not far. And that is an infinite resource.
More than 4.5 billion years ago, the solar system was formed from huge clumps of ice, dust, and rock left over from the creation of the universe. These clumps, called planetesimals, collided, growing in size as the larger planetesimals drew in smaller objects. Planet Earth was born from these molten collisions. The smaller objects not absorbed during the planet creation process were drawn to the outer edges of the solar system. There, just over 3 light-years away from the Sun, these comets and asteroids turned into an immense cloud called the Oort cloud. The solar system, with its sun and planets and stars and Oort cloud in tow, circles the Milky Way galaxy once every 225 million years. However, the 200 billion stars in the galaxy don't follow uniform circular orbits. They shift with each revolution. That sometimes brings the Sun and the Oort cloud into close contact with other stars and interstellar clouds. These close encounters can disturb the Oort cloud, spinning comets trailing long tails of cosmic debris out of their normal orbit and directly into the Earth's path.
These occur when a star comes very close to the Sun, perhaps within 3,000 astronomical units, where an astronomical unit is the Earth's distance from the Sun, or when we encounter a giant molecular cloud in the galaxy. These are very large clouds of interstellar gas where stars are forming, and these can really shake up the Oort cloud and throw many, many comets in what we call a comet shower.
These comet showers figure into one of the Aboriginal myths of creation. For some Aborigines in Australia, this is their holy land, the birthplace of humankind, a link between Earth and the heavens above. For these Aborigines, each star in the Milky Way is a dancing goddess. The legend goes that long ago, one of the goddesses lay her baby in a cradle to rest. But the cradle rocked, and the child fell to Earth. The impact left this jagged 3-mile-wide crater in the desert of the Australian interior, and, so the story goes, created life. Scientists of today think those Aborigines may well have got it right. Impact craters like this sprinkle the globe, evidence of massive collisions between asteroids and comets and planet Earth. Scientists now believe these stellar collisions brought to our world organic elements of life from deep in outer space, creating the rich and varied tapestry of living organisms we've come to view as what makes Earth unique in the universe.
Hey, that's 2-8. Okay.
Instead of photographing Soviet missile silos, this former U-2 spy plane roams the skies above, collecting dust. Space dust. Earth's atmosphere is full of microscopic material shed by passing comets. While cruising at 65,000 feet, 12 miles high, the pilot will deploy these oil-coated plexiglass plates. For every hour aloft, one of these plates will catch just a single particle of space dust. These particles are debris coming off the trail of asteroids and meteorites. Called micrometeorites, they weigh a mere 1/1000th of a gram, hitting the Earth at a rate of 1 particle per square meter per day.
Well, the particles have told us a very interesting story.
University of Washington astronomer Dr. Donald Brownlee is the father of micrometeorites. Brownlee believes these dust particles, also known as Brownlee particles, hold the answer to the origins of life on Earth.
These, we believe, are the most primitive materials in the solar system, and they are materials that are created along with ice to form cometary bodies and also perhaps asteroids in the early solar system, and they are in fact preserved pretty much in the shape that they were when they formed 4.5 billion years ago.
Brownlee is searching for microscopic organic materials embedded within the Brownlee particles. Organic materials from deep space that may have been the first living material to arrive on Earth.
So they have a very large organic carbon content, and we believe that this carbonaceous material is certainly a major contributor to organic material on the Earth. Right now, at present times, there are thousands of tons of this organic material falling on the Earth every year. And early in the history of the solar system, when life was forming, about 3.9 billion years ago on Earth, the flux of this material was probably even much higher. So this has been a natural source of organic material falling on our planet throughout its history. And it may have played a major role in the origin of life, we actually don't know.
To understand the role early comet showers may have played in bringing life to the planet, scientists look first to the Earth's cosmic sidekick, the Moon. The lunar surface is completely pockmarked with craters. Each divot indicates where an interstellar object, such as a comet, crashed into the Moon's surface.
The Moon is close to the Earth. We're like father and child. And whatever is happening on the Moon is happening here on Earth, too. The problem with the Earth is that we have erosion. We have the atmosphere. We have plate tectonics. There's not much of a record left from the last 3 billion years on the surface of the Earth. But our neighbor, the Moon, preserves a beautiful record of everything that's happened to it over the last 3 billion years. So the presumption is, and nobody disputes this, that the impacts on the Moon are a good reflection of what's been happening on the Earth. And that's really what our interest is.
When the U.S. spaceflight Apollo 14 touched down on the Moon in February 1971, astronauts Alan Shepard and Edgar Mitchell scurried through the gray lunar dust collecting geological samples from craters on the lunar surface. Discovered within these samples were a multitude of microscopic glass beads. When a comet hit the Moon, the lunar rocks melted and scattered. When the liquefied fragments cooled, they solidified into these tiny glass droplets. Richard Mueller's team of researchers at Berkeley are dating these glass beads, enabling them to determine the age of nearly 150 different impact craters on the Moon. Knowing the age of these lunar craters gives Mueller an idea of the age of the craters on Earth. Prevailing scientific theory states that the number of impact craters should decrease over time as space debris resulting from the creation of the universe becomes less abundant. Mueller's data confirms this theory is true for the Moon, so Mueller believes it is also true for craters impacting the Earth.
Cratering comes about because there's debris in the solar system, and eventually we bump into it. The amount of debris decreases slowly with time, and so we expect the number of impacts to go down with time.
But then, to Mueller's great surprise, the glass beads began to indicate that 400 million years ago, the cratering rate increased rapidly. No one knows why.
That means the Earth also underwent this increase 400 million years ago to a level that was much higher than it had been for 2.5 billion years. Initial form of life developed in that 2.5 billion years to some very primitive life forms. But most of evolution took place during this period of 400 million years when the bombardment was 3 to 4 times higher than it had been previously. This certainly played a role in the evolution of life on Earth.
When a graph of the cratering rate on the Moon is superimposed on a graph showing the number of species on Earth, the increase of both happens simultaneously. This points Mueller to the hypothesis that diversification of new species on Earth was stimulated by cosmic impacts. The same result did not happen on the Moon because the lack of a lunar atmosphere and lunar water precluded the ability for life to form.
Many of us grew up believing that survival of the fittest meant the competition of one species with other species and the stronger species won. When this catastrophe takes place, you may be very good at competing with other species, but unless you're adapted to survive the catastrophe, you really can't endure. There's an added advantage to flexibility, to adaptability. These are just the sort of traits that, for example, intelligence brings with it. It may be that the existence of these catastrophes, impacts on the Earth, is what's driven evolution towards a higher intelligence and flexibility. The most flexible animals on the Earth right now are humans.
$250 million years ago, the continents on Earth formed one giant landmass called Pangaea. The red dots on this map show the confirmed locations of impact craters here on Earth. Over geologic time, Pangaea broke apart, and the continents drifted in a process called plate tectonics. This shifted the location of most impact craters and buried some. Despite the constantly changing geography of Earth and the withering effects of erosion, the ages and locations of nearly 200 craters have been discovered so far worldwide. 65 million years ago, it is widely believed a single comet or asteroid crashed down into the Yucatan Peninsula of Mexico, wiping out the dinosaurs. 30 million years later, a smaller impact eradicated nearly all life along the eastern seaboard of the United States.
So right here, we're standing above the rim of the crater. You can imagine that this arch of the beach here, if you could see down 500 meters beneath this surface, you would see the edge of the crater.
What today is the heavily populated area surrounding Chesapeake Bay in Maryland once was tropical forest covering the mountain slopes and lush shoreline. The sea level was higher than today, and the world was much warmer. Large rhino-like mammals and hippopotamus-type creatures had come to dominate following the dinosaurs' extinction. Just off the coast, gigantic prehistoric whales plied the oceanic waters in search of food. But then, what happened next shows the devastation a comet or asteroid traveling at supersonic speeds can wreak on Earth. In a flash of light, millions of tons of rock must have been pulverized. The 60,000-degree Fahrenheit blast sent molten shrapnel back into outer space, which then came back with devastating results.
Animals and plants in the immediate vicinity within 600 miles of the blast would have been devastated.
Locally, the region would have appeared dead, but the climatic disruption would have spread across the northern reaches of the globe. Life would return to this region only very slowly. But cosmic impacts may not be just about devastation and mass destruction. The Ames oil field is one of the most productive oil deposits in the United States. Vehicles called vibrosis trucks map the area, looking for underground oil deposits. At regular intervals, the trucks deliver a mechanized tremor of 25 tons of force down into the earth. When the seismic wave rebounds, these earthquake generators systematically map the size, depth, and contour of geologic structures beneath the surface. Information that determines the probability a given location will yield oil. When the vibrosis trucks first gathered the data and created an oil well map in 1990, the oil-rich areas below the surface outlined the contours of an impact crater 8 miles in diameter. The impact created a geological anomaly, producing a mineral resource where it would not normally be found. And it's not just oil. Impact craters around the world are the cradles of some of the richest deposits of minerals and natural resources on Earth. The Verdifort crater in South Africa has produced 40% of the gold found on the planet. The Sudbury mine in Canada generates nickel, copper, and nickel sulfide ores. The Carswell crater, also in Canada, is a uranium mine. The Reese crater in Germany produces coal. The Papagai crater in Russia is one of the world's richest sources of diamonds.
Yes, impacts have a direct control over sort of human civilization.
Dr. Richard Grieve of the Canadian Geological Survey has mapped most of the known impact craters on the Earth. He says 1/3 of the known craters harbor some sort of natural resource humans associate with economic value.
Some of them are major reservoirs, some of them produce spring waters. They're quite important economically. The craters may have helped human civilization sort of rise. Ultimately, we're only around until the next big impact, and then human civilization is gone, so they have a complete control over our lives.
What eluded scientists was exactly how the comet impacts created life on Earth. But then a cask of wine provided the clue. While working with the French wine industry in 1848, scientist and doctor Louis Pasteur made a curious discovery. As wine ages in these massive wooden casks, a blackish-purple substance grows on the back of the barrels. This material is a mass clumping of wine crystals, a byproduct of wine fermentation Pasteur called wine diamonds, known more commonly today as tartaric acid. When Pasteur studied the wine diamonds under a microscope, he discovered the crystals came in only one shape. But artificial crystals he created in his lab had two shapes. One was identical to the natural tartaric acid crystal, and the other was its mirror image. The two forms were similar but different, much like left-handed and right-handed mittens. Because of this, Pasteur termed them left-handed and right-handed crystals. The two synthetic crystal molecules look almost identical, but in fact are impossible to superimpose, just as it is impossible to put a right hand into a left-handed mitten. Since the natural wine diamond consisted of only left-handed crystals, Pasteur concluded that molecules associated with life are structured exclusively with a left-handed design. Today, we know the cells of living organisms, from blood cells to bone cells, consist of biological chemicals called proteins. A protein is made up of 20 different types of amino acids. Since nearly all living organisms on Earth, from bacteria to humans, make proteins only from left-handed amino acids, left-handed amino acids are the building blocks of life as we know it. When the Murchison meteorite smashed into the interior of Australia in 1969, evidence was found that life-forming left-handed amino acids may have originated in deep space.
The drive was just really the recognition that the meteorites might provide us the opportunity to throw some light on a really fundamental question.
Arizona State University organic chemist Dr. John Cronin and his colleague Dr. Sandra Pizzarello realized that finding amino acids within the Murchison meteorite would point to a relationship between life on Earth and life in deep space.
If the organic compounds on the primitive Earth came from outside the Earth, if they were delivered to the Earth by meteorite or dust or cometary infall, then this organic matter would have already had the beginnings of this excess of one-handed forms over the other, as we see in the amino acids.
From deep within the meteorite, Cronin and Pizzarello extracted amino acids not found on Earth, amino acids that were predominantly left-handed, the kind that could give a kickstart to life.
What we find in the meteorite is that there are small excesses of one-handed form of amino acids over the other. In other words, there is the beginnings of a selection process represented in this material, which was brought to the Earth from outside the Earth's sources, like cometary or small body or dust infall, a small excess of one form of the amino acid over the other, which could presumably have been amplified and bring us to a situation much nearer to what we find in life today.
This discovery points to the idea that Earth's life forms originated not here, but somewhere else in the universe. and the same cosmic processes that may have helped life arise on Earth could also be seeding life elsewhere in the universe. The journey of discovery begins with mathematician and astronomer Galileo Galilei. In the early 1600s, Galileo searched the Italian night sky around the planet Jupiter, recording what he saw in his handwritten notebooks. The circle at the center is Jupiter, orbited by 4 moons indicated by asterisks. Galileo's discovery of Jupiter's orbiting moons led the astronomer to believe in the Copernican theory that everything in the universe does not revolve around the Earth. For his efforts, the Roman Catholic Church branded Galileo a heretic, relegating him to a life lived under house arrest. But Galileo fueled the idea that if Earth was not the center of the universe, perhaps other planets harbored life as well. To have life, you must have water. "70% of Earth is covered with water. It is an absolute necessity for each of the nearly 30 million species to survive and thrive here. So astrobiologists have focused their search for planets in our galaxy where water might exist. The best possibility, Europa, one of the 4 moons of Jupiter discovered by Galileo. "400 years after Galileo's discovery, the United States sent a space probe named after Galileo to explore Jupiter's moons. The images the Galileo probe transmitted back to Earth revealed Europa is covered with a layer of ice, presenting the possibility of a huge ocean, water, lying below. The probe's photographs captured these scar-like formations all over Europa's surface. These fractures, called double ridges, look very similar to cracks in the ice covering Antarctica.
Okay, well, let's talk a little bit about these ridges, guys.
Dr. Richard Greenberg of the University of Arizona realized these double-ridged cracks could only be made with the help of an ocean hidden below. As Jupiter exerts a massive tidal force on Europa, it pulls apart the surface ice and creates a colossal crack.
As Europa gets closer to Jupiter and further away every 3.5 days during its orbit, the shape of Europa changes. It gets longer and then shorter, longer and shorter. Naturally, this stresses the surface and it creates cracks. Once you have one of these cracks, the tides continue to work the crack. So you'll have a crack in the ice, and the tides will cause the crack to open and close every day on Europa, every 3.5 days on Earth.
This break in the miles-thick ice allows the water below to gush up. As soon as the water is exposed to the sub-freezing temperature on Europa's surface, it skims over with ice and slush. The crack then closes as Jupiter's periodic tidal force subsides. This squeezes fresh ice to the surface along the crack. When the crack opens again a few hours later, the new ice remains piled on each side. As the process repeats day after day, it builds a double ridge of ice piled along each side of the crack. Europa is about the same size as the Earth's moon. It is bombarded by radiation, and so far from the sun, the surface temperature reaches 260 degrees Fahrenheit below zero. The ocean, however, may only be a few miles below the icy surface. And though frigid, a potential wellspring of alien plants and animals.
So you might imagine plants growing in that zone where they're deep enough to be safe from radiation, but close enough to the surface that the sun can give them energy. Now, remember what makes the ridges. What makes the ridges is this crack opens and closes every day. And so water comes up and gets squeezed to the top, making ridges. Well, as the water goes up and some of the water goes down every day, this region is bathed by warm water coming up and going down, mixing oxidants and fuels and the chemicals below. This is just the sorts of condition that life needs. There's a disequilibrium chemistry, you've got warmth, you've got a flow. So you could imagine organisms taking advantage of this setting.
I mean, if you're going to go through a whole reconfiguration process...
NASA astronomer Richard Terrell wants to find them.
The main objective is to confirm the existence of a liquid water ocean beneath the surface of Europa. It's also to go there and to understand the surface processes and to look for potential areas where the surface is young and potential places where we could land a lander in the future. The tremendous excitement with going to Europa is the potential of a biological environment. Here's a world 5 times further away from the sun than the Earth is, which has an ocean of liquid water. And it opens up our thinking to further biological environments. Energy, liquid water, and organic materials on Earth, those same ingredients gave rise to life in less than 1 billion years. Well, that same organic soup has been cooking on Europa for 4.5 billion years. So potentially, Europa is a very, very exciting biological target.
Does this mean there really are things living there? Well, we don't know. But biologists who are studying the extreme environments that things live in on Earth are saying more and more that if you have a habitable environment, then things are there.
The answer will hopefully come in the next decade, when NASA hopes to send another mission to Europa to land on its icy crust.
The Europa Orbiter is going to be the most difficult mission ever undertaken. And the reason is, first, Jupiter's very far away, 500 million miles from the Earth. Secondly, you have to get down into this gravity well, which is Jupiter. It's a hard navigation problem. And thirdly, most importantly, is Europa exists in a very, very dense, highly deadly radiation environment. In fact, a human being, a shielded human being, would die in about 10 minutes on the surface of Europa. So it's a very, very difficult place to go. We will have Europa in our future and in our children's future. The idea of exploring Europa is not going to go away. Our kids are going to be exploring Europa. And sometime in the future, we are going to be sending a submarine down below the crust of Europa into an alien ocean searching for life. And that's a very, very exciting prospect.
The search for life in the universe is not restricted to one icy moon 500 million miles away. Closer to home, there is a target that has long captured the fancy of Earth-bound dreamers: Mars, the red planet. At its nearest orbit, it's only 35 million miles away, the closest planet to Earth in the solar system. When the weather is clear, it can be seen shining brightly like a star in the night sky. Nearly 100 years ago, astronomer Percival Lowell built his own observatory so he could dedicate himself to the study of Mars. Lowell observed a pattern of dark stripes etched into the Martian surface. He speculated that some willful life species built canals in an attempt to move water around a slowly dying planet. The idea of a race of Martians captured the imagination of the public.
Well, Percival Lowell had a good imagination.
Astronomer Dr. Adam Bruckner of the University of Washington doubts any form of life intelligent enough to construct canals ever lived on Mars.
Earlier in the 19th century, an Italian discovered what he termed, called canali, which really he meant to mean channels, and somehow that got to be interpreted as canals. And the minute you say canal, you immediately think of an intelligent civilization or life that would have built them. And somehow with this in their minds, it distorted what they saw when they looked through the telescope.
Nonetheless, we set out to meet our neighbors. Fueled by the Cold War between the two countries, in the late 1950s, both the United States and the Soviet Union began aggressive space programs. The Soviet satellite Sputnik kick-started a space race to put the first man into orbit, then to step foot on the moon.
Down 2.5. Forward. Forward. 30 feet down 2.5. Picking up some dust. 1.5. 30 seconds. Forward. Just contact light. I'm going to step off the limb now. That's one small step for man, 1 giant leap for mankind.
The United States quickly dominated the race. Leading the U.S. effort was a brilliant rocket scientist named Wernher von Braun. Von Braun got his start designing and building V-2 rockets for Nazi Germany during World War II. After the war, von Braun went to work for the United States, heading up the creation of the U.S. space program. Just 2 weeks after Neil Armstrong walked on the moon, von Braun pitched to NASA a bold plan to reach Mars by spacecraft. The plan called for a Martian landing by 1982. But the United States government decided not to pursue the project, grounding von Braun's dream for the moment. While von Braun was losing in his bid to steer the United States towards Mars, the Soviet Union refocused their efforts onto the Red Planet.
To get to Mars takes approximately 6 months, depending on the particular time when you go. And roughly about every 26 months, the Earth and Mars are in the right position to be able to go there, at least with chemical propellants. It would take anywhere from about 6 to 7 months to get there, and approximately the same amount of time to come back. But you have to stay on Mars about 1.5 years for the planets to line up again so you can come back.
The Soviets wanted to know if it was possible to undergo such a rigorous journey. The Soviets started their human endurance flight tests in 1970 with the flight of Soyuz 9. Cosmonauts Andrei Nikolaev and Vitaly Sevastyanov stayed in space for a then record 18 days. But their return to Earth did not go smoothly. Neither Nikolaev nor Sevastyanov were able to stand on their own 2 feet. The zero-gravity conditions of space robbed them of essential bone and muscle mass. Further research showed that after just 5 days in space at zero gravity, a human will lose nearly 30% of their muscle strength.
When you're in zero gravity, the body all of a sudden doesn't have to fight gravity like we do on Earth. Even when we're standing or sitting, all our muscles are always working, pushing, pulling, keeping us in balance. So the body in that sense is always exercising even when we're not doing anything.
So if just 2 weeks without gravity would incapacitate a cosmonaut, the Soviets had to grapple with what effect a 7-month flight would have on the body. Would a cosmonaut even be able to function once reaching Mars?
One of the most significant problems the specialists have to solve is the provisioning of human health and a safe work environment on Mars and when returning back to Earth. A prolonged state of weightlessness should also be taken into account.
The 1986 launch of the Mir space station was the Soviets' major foray into testing the limits of long-term space habitation. Mir had room for 6 cosmonauts. Inside the space station, they worked and lived within the cramped confines of a control room, several laboratories, 1 shower, and a space-age dining room. Cosmonaut Valery Polyakov became the #1 guinea pig in a battery of exercises designed to maintain his bone and muscle mass. Polyakov followed a vigorous 2-hour workout regime, utilizing 60 different drills designed to cut down boredom. In order to receive any benefit from his daily workouts, Polyakov needed to strap himself to the floor to simulate gravity.
Моя задача все-таки сводилась еще к тому, чтобы
My task was to improve this set of exercises during the mission based on my knowledge of the system, peculiarities of the body's behavior under conditions of weightlessness, and the condition of the cosmonaut's muscles.
состояние его мышц.
Polyakov set a world record for time spent in space, 438 days, more than enough time to fly to Mars and back. On his return to Earth, Polyakov walked away from his spacecraft, mostly under his own power. He did suffer a 15% decline in muscle weight, not enough to hinder his ability to do his job on Mars if he had arrived there. But while Polyakov's body stood up to the rigors of nearly 15 months on Mir, his mind didn't do so well.
These complications exhibited themselves in petulance and obsessive fear. I missed my family. I was sad, and that lowered my efficiency.
2 months into the mission, Polyakov's daily medical reports started showing signs of mental stress, deteriorating communication skills, and rebelliousness.
It had an effect on the general background of relationships, cruelty, loss of friendliness.
It is an unusual environment for humans as a social creature. Humans are created for communication, for sharing results of success and failures. It is a problem if a human only communicates with 2 or 3 from the crew, not with big audiences. Because of that, one can have some psychological problems.
Initially, stress levels dropped as the cosmonauts became adjusted to living aboard Mir. But 2 months later, the initial stress indicators returned. As stress increases, data showed the likelihood of making errors increased as well. Being cut off from the known world while being surrounded by the enormity of space is not too much fun. A later isolation test was conducted in a Mars spacecraft simulator.
During psychological stress situations, it is useful to find ways to distract yourself from the problems.
Turns out, gardening in space provides the same benefits as gardening on Earth. The crew grew young wheat in the Mars simulator for a fresh food source. Cosmonaut Alexander Ivyansky found great comfort when he touched the wheat, especially in high-stress situations.
The scientists made a conclusion that natural elements, such as plants, could have a special influence on humans.
The cosmonauts began checking on their wheat field up to 7 times a day, spending extra time caring for the wheat and discussing the crop with each other.
It was graphic evidence that people need this contact and like it. This contact nicely influences their mood and emotional state. We had grown something with our own hands. We had something alive in the lifeless metal that surrounded us. The live plant helps establish ties with Earth, with nature. I would say that this is the essence with which the human mind is based.
While the Soviet and American space programs were researching the strains a human would undergo traveling to Mars, other scientists took a more careful look at what a space traveler would find upon arrival on the red planet.
The basic reason why Mars is considered to be the most interesting planet in the solar system other than the Earth is because it's so similar to the Earth.
University of Washington astrobiologist Dr. David Catling studies the Martian atmosphere and surface for NASA.
It's thought to be the planet which is probably the most habitable in the solar system.
In the 1960s, the sparse details humans knew about Mars came from telescope observations. There was debate about the meaning of the canal-like markings scored across the planet's surface. Breaking down the light emanating from Mars revealed the planet's atmosphere is thin and cloudy, dominated by unbreathable carbon dioxide gas. Photographs radioed back to Earth from robotic flyby missions revealed a desolate world, pockmarked by impact craters much like Earth's barren, lifeless moon. The landscape is blanketed by a thick, reddish-brown dust. The dust gives the planet its ruddy hue in the night sky. And even though the planet's temperature swings from 80 degrees Fahrenheit to a deep freeze of minus 207 degrees, hope of finding life still lingered.
An environment which is similar in some ways, but very different in others. And the principal difference is the fact that it's cold and dry compared to the Earth.
Mars is half the size of the Earth and has 1/3 the gravity. The planet is tipped over at a 25-degree angle, similar to the Earth, setting up, again like Earth, 4 different climatic seasons. And the red planet's day is 24 hours, 37 minutes long. The planet's surface is also distinguished by geological features similar to Earth. Near Mars' equatorial region is the Valles Marineris. This massive canyon would stretch from New York to Los Angeles and runs 31,000 feet deep at its lowest point, nearly 6 times as deep as the Grand Canyon in Arizona. And breaking through the thin Martian atmosphere is the Olympus Mons, 17 miles high, 3 times taller than Mount Everest. Olympus Mons is the tallest volcano in the solar system. But the question long vexing scientists is whether there is, or ever was, water on Mars. And so too, the question of life on Mars.
There are sort of 2 camps. One camp saying that Mars was once warm and wet, and the other camp saying that Mars has never really been wet, it's always been dry. And so it certainly will make a big difference as to whether life can take root if Mars was never warm and wet and if it was always a dry, kind of a freeze-dried planet the way we see it today.
The Viking missions in 1976 filled in more details. 2 orbiting spacecraft and 2 Martian landers beamed more than 55,000 portraits of Mars back to Earth over the next decade. Of particular interest are these photographs of undulating lines running between craters. They run together to form one thick line, much as a tributary system of streams and creeks meet and flow into a river on Earth. Other photographs revealed evidence of what could be traces of huge floods. The top of this valley appears to have been formed by a confluence of rushing water, carving a wide channel extending more than 60 miles across the Martian surface.
When we look at the channels on Mars, we find that the most striking ones emanate from the canyon region around Valles Marineris. To create these very wide channels going for thousands of kilometers requires an awful lot of water. There are analogues on the Earth to these channels. For example, in eastern Washington state, there's an area called the Channeled Scablands. But that, in fact, is dwarfed by what we see on Mars, that we would require 10 to 100 times as much water as what was required in eastern Washington to make these channels on Mars.
In 1997, the Mars Pathfinder touched down on Mars. Photos from the lander show a landscape littered with rocks and boulders.
There appeared to be pebbles and cobbles that were somewhat rounded, and some of the rocks appeared to be perched as if they'd been deposited in a big flood. And so these indications were taken to suggest that this was, in fact, verification of a large flood channel. You can also look at some of these rocks, and their lower surfaces is covered in dust. And that suggests that perhaps they've been exhumed by the wind. So we also see signs that the wind has had a large effect in this region as well. So we have to try and disentangle what's been caused by the wind and what may have been caused by water.
Further evidence comes from a valley at the base of the Hadriaca-Patero volcano. Called the Dow Vallis, photographs show clear signs of water courses in the sides of the cliffs where there is little sign of wind erosion. Researchers believe only water could have gouged the cliff faces in this manner. More than 100 rock formations like this have been found scattered across the Martian landscape. What is not known is, if there was water, where did it come from, and where did it go? Now the Mars surface is desert, cold, dry, dusty, seemingly lifeless. But appearances could be deceiving. While vast oceans of water may be the most promising incubators for life, minute amounts of water are enough for tenacious life forms to take hold. Dr. Emery Friedman has found living organisms in some of Earth's most inhospitable places. Here in Death Valley, California, Friedman finds primitive forms of life where water is extremely scarce.
What I found out is nearly everywhere on Earth there is life. And you have to look for it only carefully. And there is, of course, something which is limiting life, and this is water. Without liquid water on Earth, there is no life. And if there are even traces of liquid water, probably life find a way to establish itself.
Life forms that survive and create a niche for themselves in incredibly harsh environments are called extremophiles. These are species that find a home in surprising places like barren deserts, boiling hot springs, and frozen wastelands.
One could say that life is incredibly inventive to find ways to live at very harsh places, and also it is very tough. So you do not see, you do not need much water, and even traces of water are enough for some organisms to establish themselves.
Friedman credits his initial discovery to pure chance. He initially looked for tenacious life forms in soil, but a friend suggested that maybe the world's most extreme life forms lived in rocks.
So these are green organisms which are photosynthetic under the stones. The inside of rocks is an important microbial habitat. And that is a shelter, that is a niche where microorganisms can survive in otherwise extreme and deadly hostile environments, like in hot deserts or in Antarctica. The other one is, for instance, that soil is not the best habitat for microorganisms in very extreme environments. Yeah? And maybe also most important, that there are still undiscovered niches, undiscovered possibilities. We have to look very, very carefully, and look where you would not expect to find something, because life may be there.
Friedman has collected and cataloged microbial life subsisting in some of the harshest of Earth's environments, places that would rival the extreme cold of Mars. He keeps his Antarctic rock samples preserved in this massive freezer at Florida State University.
It took me some time to realize that life is present in very unlikely places. It took me a long time, many years, to realize this. And I became, with time, sort of bolder and more daring to look at unlikely places. I didn't find everywhere.
Extremophiles have been found in such unlikely places as this Swedish nuclear waste storage facility, 1,500 feet underground. At this tremendous depth, and with no available sunlight, microbial colonies flourish.
It's not an issue of the sun, but an issue of what is found here, inside the depths of the Earth.
Dr. Karsten Peterson of Sweden's Göteborg University may have unlocked the secret of their survival.
At first I was shocked, but I did believe that microorganisms were living under Earth's surface, and I knew that these microorganisms could survive well in even the most severe of environments. After my initial excitement subsided, I became very happy with the thought that organisms can live in this environment.
Peterson then had to figure out just how these extremophiles were able to thrive here.
Energy is absolutely necessary for living things, and in order for living things to form, oxygen and other materials are required as well. If you are a plant, you get your energy from the sun, but I think the microorganisms under the Earth are getting their energy from the gas in the groundwater.
Peterson is still puzzled by where this essential gas comes from and how it helps these cellar dwellers thrive.
This is a very difficult question. I think this comes from very deep under the Earth's surface, from the Earth's mantle, 50 to 100 kilometers under the Earth, even deeper than that. We know that gases like hydrogen and methane are being formed. This type of gas is very slow moving, but I think it does make its way to the microorganism level, and the microorganisms eat the gas.
In theory, there is enough internal energy rising up from the Earth's core to support an enormous population of microscopic life. It is thought that these underground extremophiles have a combined weight rivaling the weight of all the species living on the surface of the Earth.
The fact that the numbers are nearly the same means that there are quite a lot of living organisms under the surface as there is above the surface. These microorganisms have been around much longer than the rest of us. So what I am essentially saying is life can exist in far more places than we have all imagined at this point. If there is a possibility of life living under the surface of the planet as there is on Earth, and if this life lives by getting its energy from the planet itself instead of the sun, the existence of life or the possibility of existence of life on other planets becomes quite probable.
It's Joel Hagen's job to dream up what those life forms might look like.
I've always been fascinated with what else was going on in the solar system and what else was going on in the universe besides all of the amazing things on Earth.
While these creatures are figments of Hagen's imagination, he approaches his creations like a scientist, evaluating reams of astronomical data and piles of planetary photos.
For me, thinking about creating other life forms in the solar system was an outgrowth of astronomical painting of the geology and landscapes of other planets.
Each of Hagen's creature creations is based upon the planetary conditions where it might be found.
The fun in creating these things is not in being just fanciful and totally imaginary about it, but in following as much as possible a foundation of scientific principles and following the principles of science to grow a life form rather than just pull it out of thin air.
Hagen imagines that on a gaseous planet with no visible continents or habitable ocean, life may take on the form of jellyfish-like inhabitants. They float through the atmosphere and survive by converting temperature differences and chemicals of the gas into useful energy. A world with an extreme amount of gravity would require organisms with hardy skeletons and a very slow gait. On this imaginary planet where there is no carbon, silica-based life forms would have crystalline bodies.
One of the things that I've always been a little annoyed with in science fiction movies is that somebody will land on another planet and there's one creature living there, or one culture, dominating this planet. And I think that the real fascination in understanding life on our planet and then imagining what life might be like on another planet is realizing that these are biomes, these are ecosystems, whole ecologies where life forms interact with each other. I see a community and then I begin focusing on what the individuals might be like.
The one type of creature you won't find in Dr. Hagen's portfolio is a human-like being.
One of the ways that I sometimes try to imagine a completely different animal is to try to imagine that it has a totally different foundation of metabolism, of biochemistry, and these are pretty radical things to play with. These are very imaginary, but it's interesting to think about. How far does it go? Does it actually acquire intelligence? Is intelligence some inevitable quality that emerges? Is it an accident? Is it just another adaptation, almost like becoming faster or stronger or developing bigger teeth to capitalize on other life forms around you? Is intelligence just simply another way to catch food and reproduce?
I think that the question of whether there is intelligent life beyond Earth is essentially the same question as whether there is life beyond Earth.
At Emory University in Atlanta, intelligence expert Dr. Lori Marino focuses her research on the elevated brain power of marine mammals such as dolphins. For Dr. Marino, nature, life, and intelligence evolve hand in hand.
If you have mobile life on a planet particularly multicellular life, then that life is going to need a nervous system to sense the environment. And once you have a nervous system, you have the makings of intelligence.
The large pale brain on the left is from a dolphin, the smaller brain on the right a human. The similarities reflect a connection between mammal and man. But to be intelligent does not mean possessing mental abilities similar or equal to human beings. Dolphins are often described as intelligent because they can do human-like things.
Communication is a sign of intelligence, but all organisms communicate to a greater or lesser degree. And what we are looking for when we look for complex communication is something like human language.
Yet dolphins have a sophisticated language humans have yet to crack. That inability to decipher dolphin communication leads Marino to believe if intelligent life exists outside of Earth, it will have evolved skills humans may not even recognize.
So, do you think it's possible that there's an intelligence but we'll never know about it because it's so different from ours, we'll never be able to connect with it on any level at all?
Yeah, that's something that a lot of people think about. Maybe something on another planet might have a brain, but very differently organized according to different principles and have the equivalent of a neuron, but it may not look anything like our neurons or our brain.
So far, we can only say that, well, we're looking. We haven't found the aliens yet.
Seth Shostak is chief astronomer for the SETI Institute in California. SETI is short for the Search for Extraterrestrial Intelligence.
The idea that we should be alone in a cosmos which is enormously vast and implacably hostile. The universe is cold, it's dark, it's violent. The universe is very hostile. And the thought that in this incredible enormity that we are the only creatures able to look at it and understand something and to talk about it, that would be a very discouraging thought. That would be a depressing thought. Our search involves, in fact, trying to eavesdrop on signals that might be coming from other societies. Now, how do you do that? Well, we principally look for radio signals. We're using the world's biggest antenna. It's the one down in Puerto Rico. It's 1,000 feet across. You've seen it in the movie Contact. We use a big antenna because the bigger the antenna, the more of this cosmic static you pick up. Space produces a lot of natural radio static. The stars don't make too much radio noise, but the gas between the stars does. Makes a lot of radio static, and it just sounds like turning on your bathroom faucet and leaving it running. Psh! Not terribly interesting to listen to, but it's there. But we're looking for something that's different. We're looking for the kind of radio noise produced by transmitters. And the thing that's different about a transmitter is that it produces the radio noise at one spot on the dial.
The trick is finding that one channel among billions of channels. The limiting factor is the signal itself. As it travels great distances through space, it becomes weaker. This means the signal must be on for a very long time in order for SETI to capture it back on Earth.
Success means, of course, that we have picked up a signal that is indisputably coming from some other society, something with intelligence. I'll go out on a limb and say that we're going to succeed not 100 years from now, not 1,000 years from now. We're not talking about that, but in the next 2 to 3 decades. I think this is something that's within our lifetime.
Historically, landing experimental probes on Mars has been fraught with failure. At the beginning of 2004, just 2 weeks after a British Mars rover disappeared while attempting to land, the United States rover Spirit made its own attempt.
We have just passed 1 minute to atmospheric entry, current altitude 121 miles, current velocity 12,084 miles per hour.
Entry into the Mars atmosphere is when the first danger appears. Too shallow of an approach, the rover skips off into outer space. Too steep of an entry, the spacecraft can burn up. Landing is the next critical moment. The rover does not maneuver into a landing position using onboard rockets to slow its descent for a gentle landing. Instead, the rover is encased in a large balloon-like enclosure that absorbs the impact as the rover literally is dropped onto the Martian surface. The balloon is designed to cushion the highly sensitive technology packed into the rover structure. But a crash landing is always a distinct possibility. The best way to know what's happened 35 million miles away is if the rover fires up its computer and begins sending radio and video signals back to Earth.
It was very important for NASA to have these rovers be a success because NASA's had some recent failures in the Mars program.
What do we see? Wait.
NASA landed 2 rovers successfully in January 2004, 4 weeks apart.
That's looking down on our vehicle.
The close-up images their cameras began beaming back to Earth of the Martian surface has changed the scientific landscape.
Oh my God.
They've been a stunning success. They've gone essentially according to plan. There's been some hiccups on the surface. And they're both roving around and they're both discovering new things every day.
The rovers landed on 2 opposite sides of the planet, giving a widely varied perspective of the geology on Mars. The second rover, Opportunity, found itself inside a small crater, giving scientists the first ever look at what lies just beneath the Martian surface.
Near the rim of this crater, there are all these rocks, these light-toned rocks that basically stood out against the rest of the environment inside this crater. Not only that, you could see that these rocks were layered. And moreover, just that picture, once you had it in close-up, was enough to suggest that these rocks were not lava flows, they were not volcanic rocks, which are characteristic of most of Mars and most of the other planets. Embedded in these layered rocks are little sort of roundish objects, like raisins in a muffin.
These historic images of the Martian crust have now confirmed that water once existed on Mars. But they also point to a need for further exploration of the planet. Scientists studying Mars are now beginning to clamor for missions which would collect rock samples and bring them back to Earth to be studied more extensively in a controlled laboratory environment.
We need to distinguish, wishful thinking from reality. The importance is to know whether there was life on Mars, and that means whether or not we're alone in the solar system as a biology that developed on a planet. If no biology developed anywhere else in the solar system, then the big picture is that we're a rare thing. On the other hand, if it's the other way around, if there was life on Mars, then life on Earth is not some miracle. It's a statistical probability. So if we look at planets elsewhere in the galaxy or in the universe, around other stars, then the prospect of there being life on those planets would, I think, be improved greatly if we knew that life had evolved and originated on Mars as well.
Ultimately, the only way to know whether life exists on Mars or whether humans could live there is for humans to travel there and meet it.
Fundamentally, the biggest challenge to getting humans to Mars is money, because the technology is here. We can do it. Now, we went to the moon a long time ago, over 30 years ago, 34 years ago, and it's almost hard to imagine that it's been that long ago, but we did it. We can go to Mars too. There are some issues that need to be worked out, but we know how to get there. We know what we need to build to get there. It can be done. What happens is that it costs a huge amount of money. It may cost $75 to $100 billion. It's primarily an issue of the human will, the political will, and the money being made available to do it.
The key to spaceflight is cutting the weight of the rocket and spacecraft. Former astronaut John Connolly worked on the design of the Mars rover and the rocket that delivered the spacecraft into Mars orbit.
In our business, mass equals cost. Every kilogram of mass we fly to Mars right now costs us approximately $1 million. If you can reduce the mass, you reduce the amount of fuel you have to push it, you you reduce the size of the launch vehicle you need to lift it, and the cost of the whole mission comes down. So anytime you can reduce mass, you usually also reduce cost.
The heaviest part of a spacecraft is its fuel. At liftoff, 90% of the shuttle's mass is fuel, stored in the orange silo-like object in the center of the shuttle. For any real cost-cutting, the amount of fuel the spacecraft carries must be reduced, seemingly a contradiction since without fuel, the spacecraft can't fly to Mars and back. So Dr. K.R. Sidra of the University of Arizona wants any manned Mars space flights to only carry enough fuel to reach Mars.
And heater power is constantly monitored by you.
Once there, the astronauts would manufacture their own fuel to get back to Earth.
When you can produce almost all the consumables that you need for Mars exploration, using materials that's locally available on Mars with very little material that you carry from Earth, you suddenly open up the frontiers of exploration. Now you're able to breathe the air that you produce on Mars, you're able to drink the water that you produce on Mars, you're able to grow food out there, and for all your fuel needs, for all your electricity, heat needs, you're getting the local resources from Mars.
The key is the high levels of carbon dioxide in the Martian atmosphere. Electricity generated by photovoltaic cells would act as a catalyst to combine the carbon dioxide with hydrogen extracted from water vapors on Mars. The result is methane gas.
Light the flame on the Sabatier reactor, fantastic.
The methane gas would be used as the propellant driving the spacecraft back to Earth.
Whenever the explorers used what is available to them locally and lived off the land and conducted exploration that way, they succeeded. Mars is a new frontier, and we need to learn the lessons from history. And when we go to Mars, if we learn how to use the resources that are available there, we will succeed in our exploration of Mars.
A more controversial and potentially dangerous approach would be to use an alternative energy source such as nuclear power.
If you have a more energetic propulsion means like nuclear propulsion, then you can get to Mars in maybe 90 days, which is about half the time, and you can spend maybe 30 to 60 days on Mars and then come back in about 90 days. So it really shortens the whole trip.
It is unknown if nations and governments around the world will commit to spending the billions of dollars necessary to land humans on Mars. But if they do, the first astronauts on Mars will be faced with a blisteringly cold landscape, a seemingly never-ending expanse of barren rock and dry, reddish soil. Without their spacesuits, they would instantly perish in an environment devoid of oxygen, of vegetation, or protection against the howling dust storms that often fill the Martian sky for months at a time. Given this, the possibility of colonizing Mars for human habitation seems ludicrous. But the lure of the heavens and the adventure of exploring the stars has long been an almost irresistible motivation for many of Earth's inhabitants. And some dreamers want to go beyond space travel and advocate preparing Mars for human migration. Dr. Christopher McKay leads a team of scientists at NASA who examine the pros and cons of colonizing Mars. McKay is firmly in the wet and warm Mars camp, a true believer that Mars holds great potential for human exploration and exploitation.
We have a lot of good evidence that early in its history, Mars had water, must have had a thicker atmosphere, had more active volcanism, was very much more like the Earth. In fact, 3.5, 4 billion years ago, we think Earth and Mars would have had all the same major ecological environments on both planets.
If this theory is true, something must have happened over time. While Earth bloomed, Mars lost its magnetic field. The warm, wet atmosphere and the oceans that some believe once covered much of the Martian surface disappeared. The planet dried up and froze. Now McKay believes the very same noxious carbon dioxide emissions that threaten Earth with global warming could be used to thaw out Mars.
The gases that we put into the atmosphere on Earth which are pollution on Earth, would be medicine on Mars, and it would make the planet warm again.
The process is called terraforming, and the reality of whether or not terraforming will work is hotly debated. Terraforming research has focused on chlorofluorocarbons, largely blamed for creating holes in the Earth's ozone layer and contributing to global warming. These airborne chemicals are 10,000 times more powerful than carbon dioxide. McKay maintains that by releasing chlorofluorocarbons into the thin Martian atmosphere at a rate equal to Earth, the temperature on Mars could be pushed up 20 degrees Celsius, 68 degrees Fahrenheit. This warming effect would then encourage the planet to thaw out more on its own. The Martian South Pole has a coating of dry ice, frozen carbon dioxide, covering frozen water. As the dry ice melts, carbon dioxide could be released into the atmosphere and further accelerate the warming process. McKay predicts this Martian warming would happen relatively quickly.
And we could probably do this push from A to B in about 50 years, and then very quickly, in a few decades, it would go the rest of the way to the warm, thick atmosphere.
As the planet warms, the hope is that there is ice frozen below the surface that will melt, furthering the terraforming process.
We know there's water on Mars. We see it in the atmosphere. We see clouds. We see water vapor. We also see polar caps, which are very significant. The trouble is that we also expect to see a lot of water below the surface. Deep below, we don't have any information, and that ice, may or may not be there. But certainly the models show that the near-surface region of the planet is the coldest and has the greatest probability of being where the ice might be.
On Earth, ice locked under the surface is called permafrost. But now, as a result of global warming, Earth's layer of permafrost is starting to melt, turning frozen tundra into swampland. On Mars, the ability to melt the permafrost will be essential to the terraforming process. It is hoped that as Martian permafrost begins to thaw, liquid water would make its way to the Martian surface. This abandoned subterranean military storage depot in Alaska shows what the Martian underground could look like. It was built right into the permafrost to hide tanks and other large weapons. Large lumps of ice cling to the walls. What is not known is how much ice exists beneath the Martian surface. Surface photos reveal large, jagged lines called polygons. Earth's permafrost regions also are scarred by polygon cracks. Kenji Yoshikawa of the University of Alaska realized the polygons running through the permafrost in Point Barrow, Alaska, are roughly the same size as the polygons found on Mars.
This is exactly like the Martian landscape. Well, of course, I've never been to Mars myself, but the images of Mars are strikingly similar to the view from here. At least, I can stand on these features.
The distance between each polygon in Alaska is about 100 meters. About the same as on Mars. By studying the physical features of the permafrost and the polygons here, Dr. Yoshikawa thinks he can estimate the amount of ice beneath the Martian surface. Using a mobile radar device, he surveys the ground beneath the polygon structures. From the surface, polygons look like depressions in the Earth, but on radar, the ice, as seen in white, is significant. Starting 1 meter below the surface, an artery of ice runs 10 meters thick. The ice layers within the polygons are formed when the permafrost contracts during temperature changes. As temperature drops, the permafrost contracts and cracks appear. Measuring the Alaskan polygons, Dr. Yoshikawa realized that cracks of the same size held equal amounts of ice. Because the distances between polygons indicate how large the polygons will be, he also believes that Mars has polygons just as large as these in Alaska.
This is a pretty big ice, sticking to rocks on both sides. When you go to Mars, I think you can find a similar structure from about 10 meters from the surface all the way down. So even though the surface looks like a desert with fine-grained sand, once you get down to a 10-meter depth, you will find these huge frozen structures. That means there's an enormous amount of ice in the Martian permafrost.
If Martian astronauts are able to accelerate plant growth and raise the temperature of the Martian atmosphere with greenhouse gases, the theory is that buried ice will melt and seep up from underground. As this water returns to the surface of Mars, some of it would vaporize and create clouds in the sky. Water vapor is actually a greenhouse gas more powerful than carbon dioxide, again, possibly working to raise the planet's temperature. From these virgin clouds, rain would fall. And the hope is that soon enough, the reddish dust that has enveloped Mars for eons would be washed away. Earth-like blue skies would hopefully appear. Martian rivers and oceans could return. If the theory of terraforming became reality, the red planet of Mars would gradually turn blue, and an Earth-like planet could be reborn.
The amount of time it would take to go from beginning warming the planet to when there was life on the planet, and maybe even trees, could be very short. It could be between 50 and 100 years, because it's just a problem of warming up a planet.
Not everybody agrees.
I'm sorry, I beg to differ. I respect these people very much. They're wonderful scientists and so on, but I think that the whole issue of terraforming Mars is pie in the sky for a long time to come. It's technically very difficult to do. It would take huge resources to put into effect, and it would take a very, very long time to actually happen, to make the changes, to try to make Mars more livable. The other thing is that we don't know what will really happen. When you start some kind of a global change like that, there are always unintended consequences.
My own opinion, and it's not everybody's opinion, is that it's probably not possible. And I say that for a couple of reasons. The first reason is that on Earth we have a natural system which helps regulate the climate. And that involves things that are unique to the Earth. The geological nature of the Earth helps regulate the climate. It helps recycle gases back into the atmosphere. Now, Mars doesn't have that. So in other words, you'd have to do that using human engineering. You'd have to simulate, effectively, what nature does for you on Earth. And I just think that as a project, that just stretches me a bit too far. In my view, it would take tens of thousands of years even to get to the stage where you've warmed up Mars.
McKay concedes that dealing with the lack of an atmosphere on Mars is the tricky part.
The big difference, though, between that planet and Earth is that planet will not have oxygen. It will just have a thick CO2 atmosphere, carbon dioxide. And that carbon dioxide would be good for plants and microorganisms, but human beings would need a source of oxygen, like a mask, as they walked around on the surface.
The atmosphere of Earth is about 20% oxygen. Oceans produce nearly 1/3 of that total. the biological machinery making this oxygen is phytoplankton living in shallow ocean waters. These microscopic creatures photosynthesize much like plants do, absorbing carbon dioxide and expelling oxygen as a byproduct. Researchers at the Marine Biotechnology Institute in Japan are attempting to grow a species of phytoplankton that carry an enhanced ability to convert carbon dioxide into oxygen. Introducing this superproductive phytoplankton in Earth's seas might reverse the high levels of carbon dioxide associated with global warming. At this lab, the researchers are culturing a type of creature called cyanobacteria. These photosynthesizers have released oxygen into the Earth's atmosphere for nearly 3 billion years, long before plants ever grew on land. When Earth was still a young planet, the atmosphere was almost entirely made of carbon dioxide. But over eons, these microscopic creatures have slowly created levels of oxygen that most higher life forms require to survive. Results indicate that cyanobacteria can make oxygen nearly 10 times faster than ordinary land plants. So, after the Martian atmosphere is warmed with high concentrations of carbon dioxide, humans could stockpile the new Martian oceans with creatures like these. With time, Martian cyanobacteria could make oxygen that future generations of humans on Mars could breathe. But oxygen-producing oceans would not be sufficient. On Earth, the majority of oxygen supply is formed by trees and plants. Tropical rainforests in the equatorial regions are often called the lungs of the Earth because they produce the greatest amount of oxygen humans breathe. So Dr. McKay is scheming on how to grow forests on Mars in the shortest time possible. McKay has targeted Mars's equatorial regions, where the climate could be very similar to the climate found in the mountain ranges of eastern Mexico. Towering high into the sky in the state of Veracruz is Mexico's tallest volcano, Pico de Orizaba. Its peak tops out at 5,700 meters, nearly 19,000 feet. At 4,100 meters, 13,000 feet, the mountain's year-round temperature hovers at 5 degrees Celsius, 41 degrees Fahrenheit. This is the temperature McKay expects a terraformed Mars would reach.
Very old, as the ones in the middle of the forest. So we would like to see how old are these and compare them with the ones below. What do you think about that?
But McKay and Dr. Rafael Navarro of Mexico's Autonomous University have discovered another problem that will impinge on Mars's ability to grow trees.
At 4,100 meters, where we are standing right now, is where we get the highest tree lines in the world. Below there, we have huge amount of trees, but above here we have very few trees, and even a little higher, there are no trees. All these growth trees is related by the activity of bugs that are growing in the soil. What they do is that they convert the atmospheric nitrogen into a fixed form of nitrogen, specifically ammonia, and this ammonia can be absorbed by the roots of the trees, and then once they get it into their system, they can utilize it to make amino acids, purines, pyrimidines. These are building blocks to make DNA and also enzymes.
Navarro's research compares soil samples taken from above the tree line with samples taken at a lower elevation. On the right is dissolved soil from above the tree line. Its faint color means low levels of ammonia, not enough for trees to thrive. Navarro believes ammonia-producing microbes in the soil are not active enough at this altitude. The culprit? The temperature. The drop in temperature at the tree line slows the microbes, inhibiting them from creating ammonia at a normal rate in the soil.
We need to wait until the soil has some nutrients that will be provided by tiny bacteria, and then the trees will be able to use this nitrogen to grow.
But Mars's atmosphere contains little nitrogen, so the microbes will have a difficult time producing ammonia unless considerable terraforming has already occurred and the atmosphere of Mars thickens to Earth-like conditions. Navarro acknowledges growing plants and trees will take time, moving in incremental steps.
We need an interdependence, and we need to begin from the lower level of the evolutionary tree. So the first step in this terraforming is these tiny microbes. They will play two significant roles. One is they will convert the atmosphere of Mars into oxygenic. And the second part is that they will fix nitrogen from the atmosphere into the soil for larger plants like grasses and moss to grow. And eventually, once the regolith has significant content of organic matter, then trees will be able to grow under these conditions. So we need to go into steps. We cannot plant the trees immediately.
Building a true functioning atmosphere on Mars will require developing a complex ecosystem rivaling the Earth's tropical rainforests in diversity. Once built, this Martian biosphere, created through human effort, would require sensitive biomanagement, something humans have been less than competent at here on Earth. And there are still huge doubts that without an Earth-like gravitational pull, Mars will not be able to sustain a working atmosphere.
All the lighter elements and gases from the Martian atmosphere, most of them have basically gone off into space. Faster moving molecules which are lighter, like oxygen and nitrogen and water vapor, they tend to escape into space. So the question is will we be able to hang on to the atmosphere? I think terraforming is an interesting concept, but as far as being practical, not anytime in the near future, not anytime even in the next couple of centuries.
It's in the nature of life that when it moves into a new environment, that it changes that environment, but also the life then evolves, and then it becomes a coevolution of environment and life. And I think this will happen on Mars as well. If we initially change the environment so that life from Earth can survive there, then what will happen over time is the environment will change, the life will change, and together they will go down a separate evolutionary track that will be different from the Earth. So we will really have two biospheres evolving in two different ways.
It is impossible for humans to re-engineer the difference in gravity between Earth and Mars. The effects of low gravity on humans would be significant. Lower gravity creates a new form of human locomotion, as the Apollo astronauts found on the Moon.
Hey, John, this is perfect with the LIM and the rover and you and Stone Mountain. And the old flag. Come on out here and give me a salute. Big Navy salute. Off the ground, on the floor.
Dr. John Charles is NASA's point man for studying human evolution in space.
When you go onto the moon, the gravity is different, and it turns out it's probably easier, instead of walking like we do, to actually sort of skip along and use both feet. You'll see the same kind of behavior, the same kind of 2-foot behavior when a large animal like a horse runs or a dog runs. That's a very efficient way of moving given the gravity field that they're in. So we probably see that kind of movement on Mars as well.
The longer humans spend on Mars, the more their bodies will probably change in shape and function.
The effects of a long period of time on the surface of Mars or on the Moon are still questions to be answered. Essentially, we can assume that the changes in the human body will be either someplace in between the effects of normal gravity and weightlessness, or that they will actually mimic weightlessness in some regard.
The Soviet studies on Mir documented how human muscles grow weaker and bones lose density and strength during extended periods of weightlessness. Now there is evidence that low-gravity environments can damage the human heart.
Well, our bed rest experiment is specifically designed to look at what happens to the heart itself in bed rest.
Dr. Benjamin Levine heads up an experiment at Presbyterian Hospital in Dallas, where healthy volunteers spend days lying in bed doing nothing. In a vertical state, blood tends to pool in the lower extremities, forcing the heart to work harder to keep blood circulating. But lying down horizontally means the heart is less stressed. Lying down simulates a nearly weightless condition because gravity pulls at each part of the body equally.
As the heart adapts to being in bed, is that it gets smaller. It gets smaller and less distensible. That means when you try to fill it, it doesn't fill as much.
After 18 days, the physical changes in the heart muscle are significant. On the left is a cross-section of the heart before the experiment. To the right is the thinner, smaller heart after bed rest. The muscle itself is 5% lighter. In another bed rest test lasting 3 months, the heart dropped 16% of its muscle weight. So the more time a human spends on Mars, it is likely the more physical changes could occur.
The next question is, that's only one generation. What about 10 generations, or 20 generations, or 100 generations? Well, that's evolution. That's relevant not for us, for you and I, traveling to Mars, but for our children's children's children. And maybe they will develop new kinds of skills or new capabilities that we can't even imagine. And nobody will know that until we get there.
Other evolutionary changes might occur as well. Scientists speculate that brain size could increase, our dietary patterns could alter, and sleeping habits could modify. Over time, maybe it will be more accurate to identify Martian humans as a different species than Earth humans.
I think that the view of Earth from Mars, the view of the blue dot, the original blue dot, will be sort of like the view of a child looking at their parent. Always have love and respect, but realize that they must go their own way. And so life on Mars must go its own way, and it maybe have to separate eventually from Earth in an evolutionary sense. And maybe that will be the first generation of many generations of life that leave and go beyond the Earth. And I think the fundamental question that I'm interested in is, what is the role for life? What is the future of life? And I see Mars as the first testing ground of the possibility that life has a future in space.
Science has now established the case for life having begun in outer space. New discoveries inch us closer to determining whether life exists outside of our Earth. These discoveries only serve to renew human desire to travel into the unknown realms of the universe. And humans have developed the knowledge and the technology to take the next steps in a journey through the solar system. But at what cost? Earthlings have become more blasé, less enamored with the excitement and challenges space travel presents. Priorities have changed. With the misery of poverty and hunger and environmental ruin facing the Earth, many question the wisdom of spending billions of dollars voyaging into the dark void of the sky, creating new planets for human habitation. Humans will soon need to decide how important it is to uncover the mystery of whether there is life beyond Earth.
For more information on Exploring Space, The Quest for Life, visit pbs.org. Exploring Space, The Quest for Life is available on videocassette or DVD. To order, call PBS Home Video at 1-800-PLAY-PBS.